Yes, now you've been great so far, and now the other session, let's do some deep Python learning with Erik Rehn. So give a big applause right now.
Okay, thank you very much for coming. I will show another pointless project. We are going to apply deep learning with Tensorflow to Python execution. And my name is Erik Rehn. Quickly about my background. I have a master's in computational neuroscience from the Bernstein Center in Berlin. I'm a founding partner at Slagkryssen, which is a mobile app agency here in Stockholm. And I previously worked as an AI and computer vision researcher at Vicarious outside of San Francisco. And currently I'm at Doer, a startup here in Stockholm, where we apply deep learning to automate bookkeeping. So I work with OCR and document information extraction. So the question we are going to look at here today is it possible to use machine learning to train a function to execute Python from examples? So we're going to invent our own Python interpreter, but not by writing it by ourselves. We are just going to show examples. So normally we look at programs as routines that process data. But here we're going to look at the programs themselves as data. And then we have, the programs are very simple. They look like this. A few lines of code, some if statements, maybe one or two variables, and then an output, and a numeric integer output. And the question then is, like, can we generate a lot of these programs and then apply some kind of machine learning algorithm to train on these examples, and then learn how to execute new examples that we haven't seen before. And this idea is not mine. It's from this paper, Learning to Execute, by Seremba and Suskever. They were then at Google Brain, but now they're at OpenAI, I think. And they showed how to do this. And in this talk, I will kind of walk you through how to implement this in TensorFlow. So we're going to look at some deep learning, and especially recurrent neural networks. And then a very quick implementation in TensorFlow. And hopefully, I will convince you that implementing deep learning models nowadays is very simple. Yes. So TensorFlow was open sourced by Google in November 2005. I actually don't know which license they use, but that's interesting. It's all about defining computational graphs. So you have a graph where the nodes are mathematical operations, and the edges are tensors, or multidimensional data arrays. So if you have worked with the NumPy before, the ND-array class is a tensor. But the difference here is that we actually create a graph, and I will explain later why. And it has support for distributed computation on multiple CPUs and NVIDIA GPUs since the latest release, which was released, I think, 1 or 2 months ago. And it's heavily inspired by Theano, which is another Python library, mostly developed at University of Montreal, and Torch, which is written in Lua. But I would say, like, now that TensorFlow has matured a bit more, it has a much nicer and friendlier API than Theano, and you don't have to learn Lua. Hooray. Right. So the problem we're looking at here is this. We want to learn some neural network, which is just a function, basically. We can call it execute. And we should fit in strings of programs, and it should return an output sequence, which is the target. And this can be framed as a sequence-to-sequence problems. We have a variable length input sequence and a variable length output sequence. And in machine learning, this is called supervised learning. We have some input and we have some targets. And we have lots of them, pairs, input-target pairs. In our case, the the X here is the program, and the target outputs, the Y's, is the Y's, yeah. Right. And for this, we can use something called a recurrent neural network. This is in its simplest form. To actually solve this problem, it will be a bit more complex, but the ideas are the same. And this is how the graph looks from a TensorFlow perspective. We have some input, xt. So we have a sequence of 1 to capital T, for instance, long sequence. And for every time step, we have an input, xt. And then we have some function, which is a sum of two linear transformations. So it takes xt, multiplies it with some matrix, and computes a hidden state or the cell state at ht. And we also use the previous cell state at the previous time step. So ht here is kind of the internal memory of the recurrent cell. So at every time step, we feed back the cell state and do this computation. And then we have some nonlinear function we call here s. It's just a squashing function that makes sure that the values are between -1 and 1 or 0 or 1, depending on how you choose it. And then at the output, we just have a linear transformation to create some output symbol. In this case, we only have one time scale. So the inputs and the outputs have the same number of time steps. And that's not what we like, right? Because the targets are much shorter than the input sequences or our programs. So then we can use something like as we call a sequence-to-sequence model. And it contains actually two recurrent neurons. One is called the encoder, another is the decoder. So we run the encoder, we feed in the input characters one by one. So here I've presented it like an unfolded view of the graph. So these are basically recurrent connections. So these arrows represent the hidden state at each time step. So we basically feed in the inputs to one recurrent neural network, and then when we have fed in the whole input sequence, we transfer the hidden state to another recurrent unit, and also give it a go symbol. And then it kind of decompresses that hidden state into the target sequence. So you could view this as like, you feed in the input, you create one fixed length vector, and you give it to the decoder, and that kind of decompresses that or generates the target. Right. So I hope you can follow this a little bit, at least. I will later show you the implementation. Hopefully it gets a little bit more clear. So yeah, why not just use NumPy? The purpose of using TensorFlow or something similar is graphs let us do automatic differentiation. And these models are trained through gradient descent. So we have to compute the partial derivative of all the parameters in the models, these weight matrices, with respect to the loss function. Or we have to compute the derivative of the loss function with respect to the parameters, sorry. And TensorFlow does this automatically for us, so we don't have to use pen and paper to compute all the derivatives. We just have to define the graph, and it does it for us. Because this space can be very high dimensional, so this is just an example of a three-dimensional space where we do gradient descent. But a model might have millions of parameters, so it gets nasty. Okay. So yeah, we want to operate on sequences of letters, right? For our programs, and the simple way to encode those are just 1 of k encoding or one hot encoding. So for every symbol, we just put a 0 or a 1 in a 0 vector, for the index of that symbol. And that will give us our input vectors and also output vectors. Right, so now it's some coding time. Let's see if we can show you. Can you see this? Right. So I used to prepare a small notebook here where we kind of walk through the code. So this is the graph we want to construct. We have a number of input time steps for the encoder and some output steps for the decoder and some also input steps for the decoder. And then we will like to wire up this graph. And each of these nodes is just a linear transformation, basically. We have some weight matrix that we multiply with the hidden state and the input vector. So we start by importing Tensorflow. And fortunately for us, Tensorflow already have some sequence-to-sequence API implemented and some recurrent neural network code there, so we don't have to do that much ourselves. We just have to choose how to wire it up. Now I realize it's the resolution here is quite low, so we might not be able to see everything, but I think that's okay. Okay, and then we define sequence-to-sequence model. And I've just made this as a class. We have some input parameters. It's the batch size. So when we train these models, we feed them with a batch of input patterns. So for instance, in this case, we can give it 32 input programs in one batch. And then it will process them and update its parameters, and then we go for the next batch. So this is normally something like 32 or 128 or something. And then we define a maximum input sequence length and a maximum output sequence length. The number of symbols we have in our alphabet. So we will just have the lowercase letters and some symbols like colon and so on, and the numbers. And then we have a flag that says if we're creating a training graph or not. And the reason for that is that during training, or rather during inference, we will actually feed back the output of the decoder to itself. So it can kind of generate the next character condition on the previous character. During training, we know the target sequence. So then we will just kind of clamp the input to the decoder to that correct character. So if it does an error at the output, we will kind of correct it on the next time step. Right. So now we come to the graph creation part. So we have a number of encoder inputs, and they are just placeholders in TensorFlow called. So a placeholder is the input to the graph where we can feed in data later. And for that, we define some shape, and this is the batch size times the number of symbols. So the number of symbols is the size of the input vectors we have. And then we have the decoder inputs, and these are the same essentially, but there are just 6 of them instead of 70. And we add 1 extra here. Hope you can see that, +1. Because we have to feed in the go symbol at the start. Okay, and then we have some linear transformation here at the output. So we create our weight matrices for that. We call it W out and also some bias. So this is just a one-dimensional vector that has the length of the number of symbols. And we also define the number of hidden units that we will use for our RNN cell. And this is basically the size of the hidden state. Here I've just shown some small number. For the real demo I will show later, we have 10 times as many hidden units. Right. Then we have a function that does the looping of the output. So as I said before, during training, we have no looping, but during inference, we loop back the input. And that's what we have here. And then we define what kind of cell we want. TensorFlow has a lot of code for different types of RNN cells. Here I used to find the basic RNN cell, which is the simplest one, which I showed you before. Okay, and then we create an RNN using the cell type we have, give it the encoder inputs. Basically, this is what we're wiring up now. We get the final state of the encoder, feed it into the RNN decoder, give it as an argument here, and then show it, also give it to the decoder inputs. And here we have the part that if you're creating a training graph, we have a loop function, which is what we have here, which basically will feed in the output of the previous step, if you're not training. And then we just wire up the output linear transformation. Okay, so that's basically it to create the model, the inference graph. For the training part, we also need to do some extra steps because we have to define a loss function that we want to minimize. Fortunately, TensorFlow has us already implemented. So we just take all the targets, which is just the decoder inputs, but we will skip the first go one. And then for every time step, we compute a softmax cross entropy with logits, which is just, it basically just measures the difference between the input distribution, or the output distribution of the network and the desired distribution of the targets. And then we sum them up. And then we need to create computed gradients also. And then we ask TensorFlow what are all the trainable variables. And these are basically our linear transformations and the parameters of their RNN cell. And then we compute the gradients with respect to the loss. We choose what kind of optimizer we would like to have. Here's just the simplest one, the gradient descent optimizer. We choose some learning rate, which is just how far we will go for every mini batch when we do gradient descent. We give them to the optimizer, and then we just store the training operation. And the training operation is what we will run for every iteration when we train our model. Okay, and that's it. And then we need to construct two different graphs, as I said, one for training and one for testing. One example where we loop and one where we don't loop at the decoder. So we do that. Okay, that's basically the model creation. And now we need some data. And then I've written just a very simple program generator that generates programs of a certain length and where the digits have a certain maximum length also. So we generate 32 of those. That's one batch. And we can have a look at them. They look like this, for instance. Not very hard. These are a bit more tricky. Stuff like that. Okay. And then it's time for training. So we normally when you train these color models, you have you run maybe several thousand epochs. Now we define a very small model, and we will just run it for 5 epochs. And for every epoch, we will have 4 batches. So it will be 4 times 32 programs that we will train on each batch. In TensorFlow, you create the first session, which is basically a connection to the TensorFlow backend. So a TensorFlow backend can be running on like a huge cluster or something. Here it's just running on my CPU on this computer. And then when we start training, we start by initializing all our parameters, and they will just be initialized to random values. Maybe I skipped that part before, but we actually shows how to initialize them here with a random uniform distribution. And then we run. So this runs for 5 epochs. And as you can see, the training loss here decreases, as it should. And we are happy. Now we just have to run this for a long time on a much bigger machine. And maybe we will get something out. Yeah, I forgot to say that for every iteration, training iteration, we have I've written this method, fit batch, but it basically just takes the inputs, our programs and the targets, and our graph, and puts the data into the placeholders, and then run the training operation down here. Right. So now I'm going back to the presentation. So this is a plot over the error when I trained a much larger model on this project, on this problem. So instead of having just one layer of RNNs, we have 2 layers. And each cell has 4 times the many parameters. It's called a LSTM, long short-term memory. It's a RNN structure that is better at handling long-term dependencies. So we have these kind of long sequences, in our case up to 70 characters. And the output depends very much on the input. So it has to remember things over a long period of time. LSTM units work much better. In the example I showed you, we had 32 hidden units. I used 10 times the more, and that adds up to 2.6 million parameters. During training, I start off by showing very simple programs and targets, and then as soon as the network gets decently good at them, I increase the difficulty. So in the beginning, the programs have just 2 lines of code, and then I increase the difficulty to 3 lines of code and so on. And that's why you see these jumps in the validation error. I trained this with 260 epochs, or it says batches here, but it should say epochs, which so the network sees about 10 million programs, actually. But I make sure that the validation set I have is disjoint from the training set. And I do that by taking the hash of the training and look if of the program and see if the hash is even or uneven. And that's to make sure that during training, the network haven't seen exactly the same program as during validation, because then it could just memorize all the input programs. Okay, so I'm just going to show you how well it works. So here I'm running the larger one that I pre-trained. And like I said, it takes about 10 hours to train this network on an Amazon AWS machine, GPU machine. So here I have some examples. Here's a pretty simple one. Hope you can see here. So here is the target output, which I evaluate using the exec Python function. And here's the output of the network. So in this case, it got it right. Here's a bit more complex one with actually 2 variables. But as you see, quite often these if statements just evaluate to false. So there's a big correlation between the first lines of code and the output. Here's just the sum of these 2 variables. Here's a bit, yeah, as I say, here it can just output the first one, but it has to know that this is false, right? This is a bit more complex. The first one evaluates the true, and the second one to So it has to update the A variable, and then the second one is false, right? So it seemed to work quite well. It does some mistakes like this. It's sometimes you can actually see what it kind of makes for a mistake. So it's maybe evaluate some if statement to the wrong thing and so on. But in this case, I think it's a bit harder. It's just a miscalculation somehow. Yes. So that's it. We go back here. So what we've looked at here is a so-called sequence-to-sequence model. Of course, the problem we looked at is pointless. The Python interpreter works much better, is faster, more accurate, and so on. But it's an interesting experiment to do anyway. The more classical applications for these kind of models are language translation. Neural language translators are state of the art at the moment, I think. I'm not sure if Google Translate is actually implemented in that way, but it might be in the future. Another thing that might be more useful is data normalization. So for instance, you might have lots of strings of date with strange date formats. And then instead of writing all the logic to normalize them to the date format you want, you can use train a network to do it for you, if you have the data. And another application which is closer to what I'm working at now is extraction of structured data from unstructured data. So if we first OCR this receipt, for instance, we have all the text data. We can trade these kind of models to, for instance, output JSON right away. So, thank you very much for listening. That's all for me. Any questions?
Thank you. How do you suggest to avoid overfitting during this time of training and then you do testing? In your case, I mean, for example, in the last neural net, in the last layer.
How I suggest not to
yeah,
overfit?
In general, yeah.
I mean, so one thing is to have a validation set, of course, which is not the same as a training set. In my case, I use a hash, as I said, of the program to make sure we don't use the same programs during training and testing. As long as you have a validation set which is good and diverse enough, I think you can be pretty safe. Yes. Did that answer the question?
Yeah, thank you.
I have a question about, hello, here.
No, oh, sorry, too close.
I have a question about, actually, since this is a bit over my head, where do you go about to learn machine learning in the beginning? I mean, the path, a good pointer.
Very good question. There's many excellent YouTube lecture series, actually. I would say that's a good starting point. And just do something very simple, simple classification models, implement that. And yeah, YouTube is a great resource. There's also some online courses. I did Stanford AI online course some years ago. That was great. It didn't deal with deep learning at that point, but there's so many online resources for that.
Thanks.
Yeah, so a question. When I was looking at the mistakes the program made, they seemed pretty interesting. Could you understand why it made mistakes by studying the hidden layers, studying the weights maybe, and see this is the reason why it made the mistakes?
Yeah, I mean, I think you probably could. I haven't done it. This was something I hacked together for kind of this presentation. But in the original paper, they do some analysis on that, and I'm sure that you can understand. Sometimes you can see that it kind of misinterprets the if statements or stuff like that, which is interesting. I would say that this is also kind of the drawback for deep learning. It's kind of a black box procedure. It can be hard to understand what's actually going on and why it doesn't work in some cases or not. But it would be interesting to actually study how the hidden state develops over time and see which units are active and so on, and how it kind of approximates this computation, because it's obviously not doing this in the correct way. It finds some approximate way to evaluate those programs.
Does it make human-like mistakes? Since it kind of simulates a brain.
I don't know. I mean, when it comes to the if statements, they kind of look a bit human sometimes. Yeah.
Cool. Thanks.
Any more questions?
There's one over there.
Yes, maybe a bit tangential to the talk in general, but I was interested in the receipt that you were analyzing. Were you going full out deep learning even for the OCR, or were you OCRing with a OCR solution?
We actually develop our own OCR solution, yeah. So we'll be using deep learning for OCRing, yeah. Did that answer the question? Yeah, yeah.
Any more questions? Okay, thank you, Erik. That's
Thank you very much for
fantastic.
listening.
Yeah. So